I'm Xavier Vintal, and I will be doing the beginning of this lecture, the easy part. So as I said, so if you're here, you probably have a vague idea of what quant can do. I just want, in a few words, to remind very vaguely also what it can do, and then we will go smoothly with a very, very simple example explaining the mathematics actually that are behind quant and how quant actually solves them. So I will do that with a very, very boring example, a one-dimensional scattering problem. So you cannot find anything more boring than that. But try to stay with me, because then we will have all the tools to actually go to much more complex systems and solve actually real-life systems. So here on this slide, you have a few examples of problems that have been actually studied with quant out of many. And for instance, you can look at a graphene flake here, or you can look at the quantum Hall effect in a quantum point contact. This is an example we will look at in this tutorial. You can do 3D systems, you can do Majorana fermions, you can do interferometers, you can do superconductivity. So you can do all kinds of things. Here, this is a magnetic texture. And you can do all kinds of things within a very simple API, so interface that gathers everything in a as simple as we could do API. So let me get started. I will introduce essentially the theory behind this. And then once I have the basic tools, basic theoretical tools, we'll go ahead and actually see how quant actually does to actually solve this. And then later we will generalize that to more complex systems. So this is the problem I want to solve. One-dimensional Schrödinger equation. So second derivative of psi is a wave function, plus a potential that can be actually anything, like a random potential like the one I drew here, times psi equal E psi. I want to solve this, this scattering problem. And V of x is only non-zero in a finite region. Right? And this is a scattering problem because essentially for on the left region here, there is no potential. So we can solve the Schrödinger equation. Is essentially we have plane waves. We also have plane waves on the right. And here we can have like complex things. And the problem is actually how to match all this wave function, how to match a derivative on the wave function here and there to solve this issue. And then once we have done that, we will use this scattering state to compute observables like conductance of a system, for instance. So the first thing we do in quant is we discretize the problem. I mean, quant only deals with discretized problem. So in this case, we will just replace the second derivative here by its discretization form. So essentially, that's a second derivative when once you discretize. A is lattice spacing. And once I have done that, now I have psi of x only at very particular points. So an integer times lattice spacing A, and I call that psi n. And also the same for Vn. And if I call h bar square over 2ma square, like I call that t, then I arrive at this discretized equation. So this is essentially the same equation as the continuous one, but now it's on a lattice, it's a discrete equation. So here I arrive at this discrete equation using simple finite, finite difference scheme. There are many other ways to arrive at equations like that. You could, for instance, start from orbitals localized on atoms, and that would be time-binding approach, or you could do like a Vanier also approach if you want to make contact with density functional series. There are all kinds of ways to arrive at a discrete equation, but at the end of the day, you get a discrete matrix equation like this. So now instead of potential, which varies continuously, it varies discrete in discrete way, and I still have plane waves here and there. Okay, so now that I have discretized my problem, I need to solve it. So first, let me rewrite it slightly. So I just absorb this 2t here inside Vn. So Vn now is a new Vn. It's not the same one. I have absorbed it. And also I put t equal 1, which is, so I essentially write all the energies in unit of t. So it's easy to solve this problem on the left-hand side, where the potential is 0. I essentially have plane waves, exponential ikn, or exponential minus ikn, and I can actually have any linear combination of these two. Here, we will look at scattering states, and this means that we will actually decide that the incoming coefficient here, instead of exponential ikn, is 1, and we will compute the whatever reflection we have. So it's one particular linear combination where we actually impose what is incoming towards the scattering central region. So on the left, we have incoming plus reflected, and on the right, we have the transmitted with an amplitude t. And I just realized that I use the same letter t for h bar square over 2ms square and for the transmission, which is very bad, so I apologize for that. But since now it is equal to 1, you can actually forget about the above 1. So if you take a plane wave and you actually insert it into this equation with Vn equals 0, because we are on the left and the right, you find that it satisfies the Schrödinger equation, provided that E equals minus 2 cos k. So this is the dispersion relation of our 1D wire on the left and on the right. So we are almost done with the mathematics. Now we essentially are going to, so we know the solution on the left and on the right. We are going to apply this equation in the middle and also at the boundary between the scattering region and the leads, the electrons. And this corresponds, if we had if we were still using the continuous model, it would correspond to matching the wave function and matching its derivative. So instead here we will write the equation at this side and at that side, and then again at this side and at that side at this boundary. So if you write this equation at these 4 locations, so somewhere anywhere in the middle, and at the boundary between the left and the next one, or also n equal L and L plus 1, you find a set of 5 linear equations like this, which I can rewrite in a matrix form like this. Okay, so this and that is exactly the same. I just rewrote it. So you see that I have a linear problem. So it's a big matrix times a big vector that contains the value of the wave function anywhere inside the scattering region plus the reflection on the transmission equal whatever I inject. So it's given by this point. So I inject here on the left, so I have incoming stuff on the left and nothing on the right. So essentially, this is what Quant does. It sets up a system like that, and then it solves for this function. And we see that in one, so you can put that in any linear algebra routine, and you get in one call, you get both the wave function, the scattering wave function inside the system, as well as the reflection and transmission coefficient that, as you will see, are very important for calculating transport properties. So we can do the same when we have incoming wave from the left, right? Sorry, from the right now. So with reflection here R prime and transmission T prime. And we can put together all this in a matrix S, which is the so-called scattering matrix. And that's really the central object of the transport theory of quantum coherent object. So we are almost done with the theory. Now there is one last step. So now we have solved that. I mean, suppose that we have solved that. We need to calculate observables. And that means that I have to explain what is a Landau formula that relates the conductance, so something which is really we can measure with a voltmeter and posing volts on measuring currents to scattering states. So let me begin by calculating the current. So the current density would just read like that for a continuous model. So this is a discrete form. It's essentially the same. It's a discretized version. And if you calculate the current for a plane wave, you get that the current is actually, you just insert this into this formula, and you will find that it's actually exponential ik minus exponential minus ik, which is also 1 over h bar times the velocity being the derivative of the energy with respect to the momentum k. So that's for a pure plane wave. Now for a scattering state with incoming and reflected, you get the same, but now there is also your minus the reflected part. And by the way, let me note that since current in conserve, so this current is the same everywhere, wherever you compute it in the line, that current conservation. That means that actually 1 minus r square is equal to t square, so that's current conservation. And it means for this matrix S, for the scattering matrix, that this matrix S is unitary because it conserves the total current. S dagger is equal to 1, and that's a general property which is always true for any scattering matrix. So we have the current, and now we just need to fill up the states. So this is my current I. Now this is a real current. Before it was a current per state. Now I want to have the real one, the one I will observe in the lab. And I just integrate over momentum, all possible momentum of incoming state, times Fermi function for the corresponding lead, times the corresponding current that I just calculated. And I do the same for the right lead with a different Fermi function. So you see here, FL and FR are Fermi function with different potential, mu, and possibly also for a different temperature. Now we can simplify this formula a little bit. You just realize that velocity is actually dE dk. So it's the inverse of the density of state, dk dE. So actually the dk here simplifies, right? And I can also put the 1 minus r square on the t square. We just saw that because of current conservation, it's the same thing. So if I put everything together, I get current equal E over h times integral over energy, the transmission probability, so the square of the transmission amplitude, times the difference of the Fermi function in the two leads. And that's a general version of the Landauer formula. And with this, you could calculate, for instance, a current created by a gradient of temperature or a gradient of potential or a combination of the both or anything. If you look at it at 0 temperature for an in linear response, it simplifies. And then you just get current equal E square over h times the transmission probability at Fermi energy times the voltage. And this is the celebrated Landauer formula. So that's it. We have gone through all the mathematics. We have done it in a very simple case, but essentially it's not different for the arbitrary general case. I mean, the algebra is a bit more complex, but essentially all these concepts remain. So now let's see how we can actually do that in a calculation with quant. And let me clean my cells so that you like I do it. Here. So we also maybe get slightly bigger window. Here we are. So the first thing that we do is we import quant, right? So everything is written in Python. So it's very simple, very expressive language. So first thing we need is to import quant. So that's a library that does the job. And also I will import this library, pyplot from matplotlib, that actually allows us to do the plotting. And the first thing that we create is a very simple lattice, a square lattice. And we will see later examples where we use other kind of lattice, like honeycomb for graphene or things like that. And we also create a builder, which is essentially an empty system. And in this line, this is a magic line where a lot of things are done. I create sites. So if you give to a square lattice, you give it 2 index, it gives you back a site. And I create it for all possible x in a range of 20, which means 0, 1, 2, 3, 4, up to 19. So you see the quant, we actually loop through all these sites and put it into the system and actually assign the corresponding diagonal part of the Hamiltonian to be 0. And then we can actually plot this. So now let me run this cell. And I get my 20 sites here in a line. You see that there are nothing connecting them so far, so there is no hopping between them. So this is a very boring problem at the moment. So the next line here, I start to introduce hoppings between this site and the next one, right? And you see now it's only for up to 19 because I just don't want to do it to the last one. And I put this hopping to be equal to -1. And you see now that when I plot the system, I see now the hopping. So it's a good way to make sure that everything has been done properly, to plot always the system afterward. So already with this, we can do, so you can actually already branch to other libraries other than quant. And that's really a big idea of behind Python, I mean, scientific Python, is that many people provide libraries to do many kind of amazing things. And everything is intercompatible. So here I will use NumPy. It's really the basic library for doing computation in Python that allows you to do a lot of things, basic things. So this first line, I just finalized the system. So a finalized system essentially goes from the high-level representation very close to the very simple with high-level concept that we understand, and it creates the sparse low-level matrices that are actually needed for the numerics. all the ugly things that you don't want to know. And then when I have this final system, I can, for instance, ask it to get a Hamiltonian matrix, and this will actually return a matrix, like really an array, 20 by 20 in this case. And then I can use a NumPy or any other library to actually diagonalize this array and get the eigenvalues. And then I can plot them using matplotlib. And I won't go through all the details here, but here I have also the exact spectrum, which I could compute analytically and compare the two. So the circles correspond to the result of the numerical diagonalization, and the line correspond to the analytical result, and we are very happy because it matches. So far it's a finite system. Here you see. Now to make it infinite, we need to connect it to leads. So first I need to make some leads. So this is a lead. A lead is a system. It's again a builder, but that has translational symmetry. So first we create the translational symmetry here, like so, and then we create a builder, which is invariant by translation with this symmetry of the vector is -1, 0. Then I can again fill it with just one side, because now it's going to be automatically repeated up to infinity. And also I just add one hopping, and that's sufficient to create all hoppings because it will be repeated infinitely. So if I plot the system, I get something very boring because I have only one unit cell, so which is one side connected to the next. When you have a lead, you can actually plot the bond structure using quant.plotter.bonds using the finalized lead, right? And here I also added the analytical bond structure -2 cos k, which we derived earlier. And you see we have a nice match. And it's always a good idea to look at the bond structure of the leads to make sure, for instance, that you have available states, that you are not in a gap or something like that, so that you know exactly what you are doing. Now we can attach the leads. So using system.attachLead, and also system.attachLead reverse. So this is a nice trick to actually allow to have two leads with one. So it will essentially create one lead and then reverse it, the opposite symmetry, and attach it also. And now if I plot the system, you see that now I have these red things and these shaded red things that correspond to the infinite system that now has been attached. So now the system is officially infinite. It continues all the way to infinity on the right and all the way to infinity on the left. So I'm almost done. So now I need to do a real calculation. So I will create a bunch of energies, and then I will loop over these energies, calculate the scattering matrix. Upon the corresponding transmission between 0 and 1, which means first lead and second lead to this list of conductances, and then plot the result. So let me do that. And this is the result, and it's very boring. I agree with you. You have conductance, it's 0 because initially you are outside of the band, so you have no propagating channel. And then eventually it goes to 1 when you have one propagating channel, and then 0. That's because I didn't put any potential so far. So really the system is invariant by translation. It's a ballistic system. So if there is a mode, it's perfectly transmitted. And if the mode is closed when there is no conductance. So by just changing just 2 lines, we can make this system much more interesting and make it a Fabry-Perot interferometer. So now I will change the potential on this side and change the potential on that side using these 2 lines here. So you see, just decides a system of this side, and then you just assign a new potential, and that's it. Now you can change it. And now if I repeat the same calculation, all the rest is the same as in the previous cell, I will get a Fabry-Perot interferometer. So it's, okay, let me run it. It's a bit longer. And you see, you have a Fabry-Perot interferometer. So you have these resonances that go all the way to 1. That's a peculiarity of Fabry-Perot. So if you know the Fabry-Perot, the usual one you learn in optics, actually you wouldn't get this sort of envelope here. So, and this is a general feature that you get when you do numerics and you are used to analytics, that usually you get more physics than what you want. So here we have actually 2 physics. You have the physics of the Fabry-Perot interferometer, so these nice oscillations, and the physics at larger energy scale, the fact that eventually you are opening the channel and closing the channel, and the resistance of your channel when you are just open or just almost closed, each of these barriers actually has a different transmission probability. So when you put everything together, this is what you get. So that's it. We have now finished a first example, and I hope you could follow the mathematics and really see that what we do in quant is actually conceptually very simple, but it takes actually quite a lot of engineering to get the simplicity kept for much more complex systems. And now I will leave the floor to Christophe that will continue and introduce more complex part of the.
And now we are. So in this code cell, we see the example that Xavier just showed. It's just all in one cell, and I removed the parts that are not needed, like the imports. And when we look at it, well, there is the creation of the central region. Then we add the two sites that define the Fabry-Perot, and then we attach the leads and perform the computation. But observe that there is quite some redundancy in this example, because basically we are creating the same model twice. It's a very simple model, to be sure. It's basically the simplest you can have. It's a 1D chain with nearest neighbor hoppings and a single orbital, but still it is first created here in the central region. You see, I create here in this line the on-site energies are all set to 0, and here all the hoppings are set to -1. And then again in the leads we have the same. This is not very satisfactory, because imagine that the model could be much more complicated, and we would like to make sure, for example, that we have indeed the same model in both places, in the leads and in the central region. And indeed there is a way to do this, and I will show it to you at the same example. So we will do the same example, but in a different way. That's the next cell. So Xavier showed you already the concept of, I forgot to introduce myself. I'm sorry, my name is Christoph Groth. Here, Xavier already showed you the concept of translational symmetry that allows you to create a builder, a system that has a certain translational symmetry. For example, this allows me to create a lead. But such a system with the translational symmetry, we could also use it to fill some region of space. And indeed, such functionality is present in Quant. It's so here the first chunk is the same as before. We create a builder with a given translational symmetry, and we set the hoppings. And now is the new thing. We create a new builder without translational symmetry. And now we call the fill method of this builder. And the fill method expects 3 important parameters. There are some more, I think, but the 3 are, it's the model that is going to be used, then a function which is called which can be called for each site and will return true or false, depending whether the site belongs to the system or not, and a starting point. That's a site here. Lat is the lattice, and lat 0, 0 is site 0, 0 of this lattice. So what happens here in this line is that Quant will do a flood fill for you. It will start at this site and then look at the neighbors of its site, the neighbors that are connected by hoppings. And for each neighbor, it will call this function. Lambda is a way in Python to define a function inline without naming it. And in this way, you see, the function which I defined it's something which is true for sites that have an index, x index between 0 and 20. So it's exactly like what we had before. And in this way, I have only created the model once, and I'm using it in the central region. And then I could also fill the lead with this model. However, in this case, it's actually pointless to do so because a lead is a builder with a translational symmetry, but the model is already also a builder with a translational symmetry. So in the 1D case, it's a particular situation where I can use the model directly as lead. We will have later, just next, we will have an example in 2D where this is no longer the case. So as you can see here, the builder that was created by Phil, it's just a regular builder like before. I can still modify it and assign values to it. Okay, so I can execute this and I should get the same result as before. Let's see. Takes a little while. I'll already start introducing the next example. So in this very basic example, the previous one that is just running, we have a one. Yeah, here you go. It's a 1D system where all the Hamiltonian values are constants. For example, here is a constant 0, here is a constant -1. And now we are going to do something similar, but we are going to make it more advanced in several ways. We are going to use a 2D system, and we are going to use a different functionality of Quant to assign values. So let me walk you through this example. I import from the math module of Python, I import the exponential function. I will need it later for the definition of the potential. And I define two numerical parameters. One is the lattice constant, 1/2, and the effective mass of the model. Before, when we defined the lattices, here you can see that I pass the A parameter to Quant lattice square, which creates a square lattice with a lattice constant of 1/2. When the default value of A is 1, which creates a square lattice with lattice constant 1. But here I chose 0.5 to just show, to make it more generical. I also specify a number of orbitals in this lattice. This will be necessary only later. Yes. Now, here, before I told you that values were specified as constants. So a builder works a bit like a Python mapping, like a Python dictionary. You can assign values. The keys are sites and pairs of sites, and values are, for example, constants or constant matrices. But often we want to have values that are described in some functionally in some way. And Quant allows us to do this. And the term we use for this is value functions. So here you can see, it's a bit like before. We are creating a model. But this time, the model has a double translational symmetry. It's at the same time horizontal and vertical. So it's something which will allow me to tile all of 2D space. Here, by the way, note one complication compared to the case before. Before, in the translation symmetry, we simply had translation symmetry and then the real space vector, which was -1, 0, for example. And here I'm using the method vec of the lattice. SQ is the lattice. And this is a method which allows me to convert lattice space to real space. So what it will do in this case is, if I call this method, it will return the vector 0.50 because the lattice constant is 1/2. And Quant translation symmetry works in real space. You can actually use the same translational symmetry for multiple lattices if they are commensurate in the direction of the translational symmetry. So now observe that as the on-site value for my model, I'm using on-site. And on-site is actually a Python function that has been defined here. It's a Python function, just a regular one, which takes a number of parameters. And the way Quant works is that an on-site value function must always take at least one parameter. This is the site. And optionally, it can take further parameters, which are then interpreted as model parameters. So this allowed me to define a quantum point contact potential using two Gaussians multiplied with each other. So what happens here is when this function gets called, I get a site object and also the parameters. And site has an attribute called position, or rather it's a property of site. This is in this case, because we are on a 2D lattice, I can split it up into the x and y value, and then I calculate the potential I would like to have, and I return it. In this simple case, the on-site value is just a single scalar, but I could, for example, also return a 2x2 matrix. But then I should have defined number of orbitals 2 here and not 1. There is no limitation. I could have a model with 8 orbitals if I like, or 20. So I have defined the model a bit like before, and we can plot it. So I will execute the cell. And like before, it's a site which has 2 hoppings, and because there is translational symmetry, which is the hoppings connect to mirror images of the same site. Of course, it goes in not only to the left and to the bottom, but in all directions. You have to imagine that space to the plane is filled with these dots. So now let's construct the system. It's like before. Actually, we are again generating an empty builder without a symmetry. And as before, I give it a model, the model which we defined up there, and a shape function. This time the shape function is not the lambda function inline that it has been defined here. It's just a rectangle and a starting point. The starting point is needed because the system field cannot know which sites are present and which not. Must have a point to start. So now we do the same for the lead. I create a lead with a 1D translational symmetry, and I fill it again with the same model. But there is one subtlety now. We have a parameter here called voltage. You see, it's the first parameter, and this corresponds to the strength of the potential. But quant leads must be by definition translationally invariant, so the potential must be the same everywhere. And if voltage would be constant, would be non-zero, we would have some non-zero value of voltage in the leads. What would actually happen is that quant evaluates the Hamiltonian at some point in space. It will be somewhere around the origin, and then assumes that that it must be translational symmetric, and so it assumes that this potential will be like this in all of the leads according to the translational symmetry. But in order to avoid the problem to be able to set the potential separately in the leads and in the central region, which are using the same model, there is a feature called, it's a method of model. Well, model is just a builder, so every builder has this method. It's called substituted. It's called substituted because it returns a system. It returns a system where parameters have been renamed. So this here returns another builder, which is just like the one like model, only that the parameter named voltage has been now named voltage underscore lead. So by filling the lead with this modified model, I obtain the lead. I attach it twice, once from the left and once from the right. You might be wondering why there is, before we already had the symmetry -1. In principle, I could also have a positive one here, but we have in quant the convention that leads come from approach when you attach a lead, it approaches from infinity. So the symmetry direction is the one which shows, which points towards infinity. So a lead which is defined -1 comes from the negative x direction. Now I plot it, so let's check it. And you see I have a 2D system. The leads are marked with red sides. And here I've been using, so to plot a system, there's simply quant plot. And here I've been using a special option which allows me to color the sides according to something. And here I choose to color them according to the potential. So you can actually see the potential vaguely by the color of the sides. This is not very clear. There's another way to plot the potential, for example, with quant plotter map. Here we can see the potential that I have defined. And now let's look at the bands. It's always good after defining such a model to look at the bands to see what the energies involved are. To plot the bands, there is a function quant plotter bands, and a finalized system or any system has an attribute called leads, which is simply a list of leads. So here we have 2 leads, and leads 0 is the first lead. And we can see that the lowest energy is around -6. So let's pick energy -5, then a few modes are open. And now we can, like before, we can plot the conductance, but this time I plot the conductance as a parameter of as a function of a parameter. So see what happens here. I'm actually having this is called in Python, it's a list comprehension. It's like a loop which generates a list, and the loop variable here is actually a parameter. So params is a dictionary that holds the parameters. I pass it to quant as matrix to calculate the scattering matrix, and params voltage obtains all the values that are in voltages, and voltages is 100 values between 0 and -4. So I'm almost done. I will just show you one last example without actually looking at the code, because from these basics examples, you could have the impression that quant can only deal with square lattices and such things. So I will execute the rest of the notebook. Run all below. So here we are making an Aharonov-Bohm loop. Now, where is it? It's again on the square lattice. And well, I'm not going to explain this in detail, but here again, we have defined the square lattice, and we can change the lattice to something different, for example, to a honeycomb lattice. And without changing anything else, we get a ring made from graphene. By the way, these things like honeycomb and square, these are not like burned in things. The lattice module can represent any Bravais lattice. You could define some 4-dimensional Bravais lattice if you like, if you find this useful. It's just, these are just shortcuts. But if you want, you can call lattice general to generate a general lattice. And here, we can make this next example creates a 4-terminal device on graphene. It looks like a TIE fighter. You see, there are 2 leads at the top, 2 in the beginning, at the bottom, and we can also add magnetic field to it. And when we plot the transmission as a function of the magnetic field, we reclaim universal current fluctuations that you might know from mesoscopic physics. So I'm done now with the first part. And I think it's up to Anton to switch to the second part, right?
All right. So would you like to show where to find the exercises? Let's perhaps just...
Yes, I can show, and also I would like to give like a short introduction, like 2 minutes on the exercise, right?
Yes.
So
I saw there were questions in chat, but so far I think we managed to keep up. So please go ahead and introduce the exercises.
So I hope that you managed to open your binder or your notebooks locally. Then you should see.
Or in a moment you will.
Yes,
so
or in a moment you will. So yes, so try to do so now, and then you will see this index.md. This is just a notebook which doesn't have much code. It only this one cell, and otherwise it has links to other notebooks. Introduction is introduction is just what we had, and now we are going for basic exercises. So when this is open, you can click simply on basic exercises and the notebook should open. So I will do so now. A new tab opens with basic exercises. And the idea is that we now have about 45 minutes, and everybody who likes is invited to work on these exercises. The idea is that you work linearly through this notebook, so cell by cell. There are cells that explain what to do, and then there are cells where you can try to modify things. For example, here in the exercises which I made, the first cells are just to be executed, and then there is actually an exercise, and in the exercise, here later, you are invited to modify some code to try yourself, and I have followed the convention that the code which is supposed to be modified is between these markers made from 8 hash signs. Maybe no one said yet how to execute this notebook actually, so I will show this for people who don't know. So when you click on one of these cells and you type enter, it will just work like a regular enter, but if you type shift enter, it will execute the code. So I will execute now all these cells, and you see it works. The only thing is that the binder is kind of slow. So for example, this calculation of conductance, here, the plot conductance thing, it on my laptop, which is a 10-year-old laptop, takes like 2 seconds. But on binder, I think it when I measured, it took around 35 seconds. So be a bit patient with this. Otherwise, you can ask questions in the breakout rooms, and good luck.